So your final exam is from 3:30 to 5:30 on the 8th. So let's see. Let's see, other things to know about the exam. What can you bring to it? Pretty much anything you need to. It's open book, open note. That being said, open book necessarily won't be the greatest thing in the world, because it's not that we count on you relying on it. It's just that you have 2 hours and a lot of work to do. You know, so you don't want to necessarily overly rely on your book. If it's not something you know how to do, move on to something you do know how to do, and then come back to that when you have time, in case if you need to look something up. You know, just use test-taking strategies as best you can. The final exam grade is just as a warning, it's low. We passed 3 semesters. The average has been around 50 on the final exam, whereas our exams in this class, they've been around 80 for our average. Right, so our exams, we've gotten an average around 80, and when I grade the finals, you end up getting there's typically an average of 50, and it's not because the exam I feel is any harder or anything. It's just I put it down to the stress of it being a final exam, and that you're studying for basically a bunch of things all at once, and that you've got. That's what it really comes down to. It's not anything super hard or anything harder than normal. It's just that you've got an exam and you're already studying for a bunch of other stuff. That makes sense? So just know that basically, though, that being said, it goes over a lot of stuff that we've already gone over in class, and it is split half and half into basically a theory portion and half a coding portion where we actually do coding. You know, where coding is actually something that you need to. Sorry? 50. Yeah, 50-50. So 50 points for coding, 50 points for theory. So yeah, the average is around 50, 56. So just as a warning. And the reason I mentioned this is that is kind of an indication that maybe studying would be an awesome idea for that. So I'm mainly just putting that it's not. And I look at the exam and I don't think it's particularly tough or anything. It's I put it down to the fact that basically a lot of students assume that they've done pretty well in my previous exams, and so they come into the final, which we template, which is basically a group effort, right? Why does it say that I'm not plugged in? There we go. Yeah.
Did you mention or know what room the final is in?
Excellent question. I have no idea what room your final is in. That's because as a common final, I'm actually waiting to receive that information, and I will email it to you as soon as possible because we have to cram 200 students into the same room. Yes. Yeah, open book, open note. Why in the world is this not?
So we're allowed to bring our entire notebook?
Yes, your entire notebook and your textbook. So it is open book and open note. Okay? You can bring in all your material in a wheelbarrow, and I will just merely be impressed that you could get a wheelbarrow, through the very crowded halls. Okay? It's not exact. So that being said, you should probably prepare yourself a single master sheet of notes, 1 page or 2 pages of notes that are your master notes to rely on, and then anything else that you need to go into more depth, and that way, and just by preparing 1 sheet of paper or 2 sheets of paper, that will allow you to basically have something that's a quick reference, and the act of studying in that manner will enable you to, to do that, to work with that a bit better. So it's just a warning on the final exam. Now, how much time am I going to go over reviewing the class? And that's where you've got an advantage over the evening class in that regard. The evening class has the advantage that they're not taking the they're not taking the common file. They're taking something else. They're taking something that's basically got the same questions, but I put a more focus on hash tables on that one. So the big thing about let's see. So today I think I should be able to finish up with all the material that I needed to get done with. Like, because I'm just going to go over Dijkstra's algorithm, and then I'm going to go over topological sort and your last homework assignment that I'm going to go over. Technically, I'm giving you like 1.5 assignments tonight. I'm giving you a 50-point assignment on that's to, in addition to doing breadth first search and depth first search, you're going to do Dijkstra's algorithm. So it's not worth as much as the it's not worth a full assignment because it's not too much harder than depth first search and breadth first search, but it is a bit of effort. So might as well add that, to make it worth its own thing. And then the last assignment is going to be a security question, which we're going to go over. And then I'll use the remaining time in class to get started on the review, and then Monday and Wednesday next week will be review, and then I'll figure out what the heck we're doing on the 30th. Don't know if that's necessarily going to be even more review, or if that's going to be time to go over some interesting topics that I can go over, or just general ask questions, introduce you to nice, cool programming stuff. That lecture will probably be more freeform because I don't see the need to go into more than 2 lectures worth of review for you guys. And then, of course, you've got your study days. That's the other thing. That's the other thing. We've got the reviews, and then you've got a full 2 weeks to let that atrophy, unfortunately. But that's so take advantage of the fact that I record the lectures. All right. So. Yeah, so I've warned you about the final exam. Study for it. It is going to be worth 25% of your grade. In previous semesters, it had been worth nearly 35%, but because of the way that I moved timed labs around and stuff, just that works out that it's worth less now. Now, another thing to note is that I will be, you'll have your I will be there to proctor I'll be there to jump in and out of proctoring the final exam because I actually am scheduled to be present proctoring 2 exams at once. Because both 1068 and 2168 are common finals, and the common finals are all scheduled at the same time. So on the 8th, that's kind of the last day to see me. I will probably be on campus on the 9th. That's probably the last chance you'll have to actually meet with me. Because I'll probably be on the 9th. I'll be doing the bulk grading with the 1068 professors, and try to get that done. And then after that, I have to get ready to leave the country. So I will have basically my priority will be that because I leave the country on the week following the finals. So I will be focused on primarily handling that. So meeting with me in person, that should be done before the 8th. Okay. That doesn't mean though that I'm completely unavailable at that point, right? I'm perfectly able to be met via email. And this is also the point at which people start asking me about what's the curve is and the grade. So interest. I don't know if it's because I've because I don't know what it is, but the grades have been rather high this semester. Maybe that just means we had better bunch of students come through 1068, but we've had rather high grades this semester. That really doesn't impact my how I calculate my curve though, which is that essentially if you get below a 70. The curve doesn't help, right? I don't curve you to a pass, essentially. If you get below a 70 in this course, it's probably because, you didn't understand the material. And I'm not going to pass you on to the next class where you're going to fail, and then fail again. So how does that help, though? So how does the curve work for anybody else? Well, typically that just determines the cutoff points for A's, A minuses, and B pluses and B's. So what I typically do is that I look basically until there's a breaking point. Like for me, what justifies a student who gets a 90.1 and then to get an A, and then the student who gets an 89.9 to get it. So if I've got a 90.01, right, and then I've got a 89.95, what's the justification to give one student an A and another student a B? That seems rather arbitrary for a couple decimal points that could happen because of an arbitrary, an almost arbitrary mark on one student's grade or a miscalculation. That seems rather arbitrary. So typically what happens is that I look basically until there's like a significant gap. And that typically means that basically like the cutoff last semester I think was like at an 89 for A's, and then it was like 92 through 89 was an A minus like last semester I think, and then like there's typically a small gap between the A's and B, the A minuses and B pluses, and then the B's, and then larger gaps exist for anybody for the students who end up in the C range. So that's typically how it ends up. Typically, like though, if you're like in the 89 range, you'll probably get up to an A, and that if you're in the like 79 range, that will generally curve up to a B. So it just really depends on how on where the students fall, and it's like it just really depends. But the end result is that the curving will not hurt your grade. You can generally rely on if your final grade says you've got a 90, right, or above, you're guaranteed an A. If it says a B, and if your final grade calculation says a B, you're getting a B. The caveat is make sure to make sure that everything's been turned in and graded, right, and demoed. All right, so I think I've spent enough time stressing you out with that talk. So let's go and talk about like the last couple of subjects that will be on the final exam. The last subject that will be on the final exam, and then topological sort, which will not necessarily be on the final exam, but it will be on your final homework. Okay, so let's go and look at let's see. So Kaufman. Yes.
Did you mention something about maps not being on the final?
So I will probably have a question on my final our final about the maps. But it's so there will probably be one coding question, and there's definitely a coding question, a theory question about maps. Okay. So on the other hand, we need to. But on the other hand, it's so the way the common final works is I think we've said that we can each change 2 questions so that we could to make sure we emphasize the individual topics we went over. So one of my questions, I'm going to focus on maps. Now that being said, if I get lazy and don't change anything, a lot of the questions that get asked, they're being able to use a map, right? Being able to put stuff in a map and get stuff from a map and use the contains key method. That will help you like make some really concise code that really easily solves a problem, right? It's not. So that makes sense. So I'll probably have one question on that, and we'll go over review. So we went over Dijkstra's algorithm on the slides, right? And I was just putting one on the board, and I hadn't had the chance to do it, right? Right. That's what we were doing. So I'll go ahead and I'll create an example on the board of and go through Dijkstra's algorithm. So remember, what is Dijkstra's algorithm? It is the shortest path algorithm, and it focuses on the shortest path from some starting node to any other node. So it doesn't care about like a particular destination. In order to calculate a particular destination, it needs to focus it on all destinations. So let's see. Go and say we've got a node S, A, B, L, T, N, and then X. And let's go ahead and add some connections now. So A, N, B, Okay, plenty of things here, and I just kind of, I think I drew a directed acyclic graph. Well, that's a term. I think I drew a directed acyclic graph. Let's see. I think so. Okay, so first off, I just used a term there. I said directed acyclic graph, which is a bunch of words that sounds scary together, but if you tear it apart, it's really not that scary. So first off, we know what a graph is now. So directed acyclic graph is just a type of graph. Okay, directed graphs, we know exactly what that is. It just means that that the edges are arrows, right? So the directed part and the graph part aren't new. The directed graph part, that's not it. So acyclic, that's the only new word in there. So let's not focus on the A for a second. What does cyclic mean? What would you think that a cyclic graph is? Sorry? A circle. Well, what is a well? Not circle. Yeah, cycle. Yeah. So it's got a cyclic graph has cycles in it. So acyclic means what? No cycles. So a directed acyclic graph is a directed graph that does not have any cycles in it. That means that basically, if you start at one node, you're not going to hit that node again by going over any of the edges. So we can go from S to B, and then we're never going to hit S again. We're also never going to hit B again. And notice that basically one of the distinctive features is that no matter if we follow edges, we're always going to end at X. Right? So this is a directed acyclic graph. That's going to come up when we go over our final topic a bit more. But directed acyclic graphs are pretty nifty beasts. So let's go ahead and add edges to this, or add weights to our edges. So 3, 5, 1, 2, 3, 4, 7, 1, 5, 6, and 12. Okay. So rather than using S and VS, I'm going to use done as a set, and then I'm going to use to do as a set. So I'm starting from node S. Right on the exam will tell you where to start from. In to do, I will. That's all the other nodes. So it's A, B, L, T, and X. Right? And now I have to have essentially two arrays or two lists of information or two maps of information. So we have A, B, L, T, N, and X. We have the distance to them, and then we have the predecessors of them. Right? Now, initially, all the predecessors start out as our starting point node. In other words, we know how to get to each node from our starting node, S. Now the question is, how do I get to, what are the initial distances? So I start from S, and I initialize it, and this is, again, we're just in the initialization stage of the algorithm. We're not in the loop yet. So I look at all the edges connected to our starting node. I can get to A for a cost of 7, S I can get to, sorry, so B I can get to a cost of 1, N I can get to with a cost of 3, and T I can get to with a cost of 5. And everything else I mark down as positive infinity. It costs me infinite X to get there. Okay, so now for the algorithm, what do? I go and find which one I know the shortest distance to of. So for the algorithm, while there's still stuff in to do, I look for the thing that is not done that I have the shortest distance to. So that's B. I have the shortest distance to B, right? If we look at this graph, there's no better way to get to B than by using this connection. So 1. So I know the shortest distance to B. I'll move it from to do. And now I ask, do my node do the connections that B provide me with any more information? So the outgoing edges of B are 12 to N, right? So it costs 12 to get to N, plus 1 for the cost to get to B. So that's a total cost of 13 to get to N. Is that any better than the cost I currently have down to get to N? No, it's not, so I don't change it. What about the cost to get to L? That's 2 plus my cost to get to B, which is 3. So it's 3 smaller than what we have for L. Well, that's positive infinity, so that's a number. That's an actual number, and any number is less than infinity. So we'll go ahead and update L with the cost of 3, and we got there through L. So those are all of B's adjacent nodes. So let's go ahead and look at let's go through this list again. So 7, we can skip over B because we're done with that. 3, 5, 3, infinity. So we've got a tie here. We'll break the, yes?
Shouldn't have L in the third column be B?
L in the third column?
The predecessor?
The predecessor, yeah, should be B. My bad. So we've got L and N. So we can do either one we want to. Let's go ahead and say L first. So L we'll say is done. We figured out the shortest distance to L. So now let's look at L's outgoing edges. L's outgoing edges are to X. Move this 5 over here so it causes less confusion. L's outgoing edge goes to X. So it costs 3 to get to L plus 3 to get to X. So that's 6. Is that less than what we have down for X? Yes, it is. So we'll put down 6 and update the predecessor of X to be L. Okay. Now let's look. So now we're back in the choosing the next node to process. A, we found the shortest distance to, or T, well, that's 5, so that's shorter. N is 3, and X is 6. So N is the one with the next shortest distance, so we move that up to done. Let's process the edges coming out of N. The only edge coming out of N goes to X, and its cost is 5. So is the cost to get to N plus the cost to get to X. So that's 3 to get to N plus 5 to get to X. Is 8 less than 6? No, it's not, so we keep it where it is. We don't change the graph at all. Okay, so we're done here with with N. So now we go through. The cost to get to A is 7, cost to get to T is 6, the cost to get to T is 5, the cost to get to X is 6. So we choose T next. So we're done with T. We figured out the shortest distance to T. Okay. Why did I say that it's 5? It's 4. I've got 4 up there. Doesn't change our answers though. I made a transcription error there. So 4. So let's go ahead. So let's look at the edges coming out of T. We've got one edge that goes to A and one edge that goes to X. So let's look at the edge that goes to X. That would give us the distance to get to T, which is 4, plus the distance to get to X, which is 5. 9, is that less than 6? No, it's not, so we don't change the way we get to X. What about to A? Well, currently we have 7 for A, and we have 4 to get to T, and 1 to get to A. So that is a cost of 5. That's better than what we have down for A. So we're going to put down that we get to A for a cost of 5 using T. And those are the two edges that come out of T. Now we've got 5 for A and 6 for X. A is the shortest distance. So now let's look at A's edges. We've got 6 that goes to X. Does 5 plus 6 is 11? Is that right? The distance to get the cost to get to A is currently 5. Right? It's not 1, it's 5. So we've got another edge from A to X, so that would be 5 plus 11. Sorry, 5 plus 6, which is equal to 11. Is 11 less than 6? No, it's not, so we don't change our node. And then the last node is X, and it has no outgoing edges, so we're done. So now our shortest distance basically is it costs 5 to get to A. We get to A by T. How do we get to T? Well, the predecessor of T is S, right? That makes sense. So we know how to. So the predecessors, the reason we keep track of them is that it tells us the path by basically tracing the predecessors back to the starting node. How do I get to T? Sorry, I get to A through T. I get to T through S. I get to L through B. I get to B through S. And then all the other nodes, I can just go directly to, I get to X through L. I get to L through B. I get to B through S. Right? It helps me. What this does is that it traces the path. It gives me the shortest path here. That makes sense to everybody? What?
Just said from where we're starting at S.
Yes, we all. So my examples, I always start from S for starting node. We'll tell you what node to start with in other examples. Now, again, Dijkstra's algorithm doesn't really perform correctly if you've got negative edges in there, because you could create a negative cycle, or you could, having a negative edge basically could render a previous part of the algorithm invalid, right? Question? So we'll go over Dijkstra's algorithm again in the review, because we'll go over a lot of what other people have, a lot of other, we'll see what kind of questions get asked about Dijkstra's algorithms on exams, and we'll, just go over those. So now I want to go over the last topic that I feel necessary to cover, which is topological sort. Oh, actually, sorry, one last thing. What is the cost of Dijkstra's algorithm? Almost forgot that. So this algorithm, basically the initialization that takes, you have to do this step for every basically vertice in there. So this takes v time. But this loop over here, basically it's a nested loop. So while VS is not empty, in other words, for every node that's not a starting node, look at all the nodes in VS and find the smallest one with the distance. So this takes O of V minus 1 time, and this inner for loop takes O of V minus 1 time, then O of V minus 2, O of V minus 3. Essentially, it's V times V times, which means that the overall algorithm takes O of V squared time, as written here. There are faster times for Dijkstra's algorithm that use heaps and stuff. In fact, you can get it down to a quite short time, to a much more efficient time. But for right now, it takes the number of vertices squared, or at least the original algorithm that Dijkstra came up with this table that we laid out. It takes OV squared time. All right. So let's go on to the last topic, which requires me to back up the slides just a second. And this is the last topic we'll go over for your homework. So, sorry, this is the last topic, and it's going to get covered on your last homework. So, topological sorts. So, going back to the idea of a directed acyclic graph, it's just a graph. It's a set of two things, of things and the relationships between those things that doesn't have any cycles. Okay? The idea here is that once you pass through a vertex, there is no other vertex that you come back, that you don't get back to that vertex. An example of this is course prerequisites. Figuring out whether a student has the qualifications to take a certain course, whether they meet the prerequisites, that is a graph problem. Specifically, it's a topological sorting problem. Well, it's a topological sorting problem to basically give you a series of classes to take. To basically give you the sequence of classes. But figuring out whether or not you make the prerequisites, that's a graph problem. For instance, in this imaginary thing, or maybe it was something that was written for, before, maybe a couple of decades ago, this prerequisite chart, you have Calc 1, that's a prerequisite for Calc 2 and 2 computer science courses. Now this computer science course is a prereq for, in both these computer science courses, you have to take both of them because they're both prereqs for all these courses. But these 2 computer science courses, you have to take for the 2000 level electives. And CIS 166 is only a prereq for this class. You only need to take this if you're planning on taking this next semester, right? So this prerequisite chart is a directed acyclic graph, and figuring out what order you should take stuff relates greatly to the topological sort of the graph. This is another directed acyclic graph. So notice that there's no cycles and that everything leads to 8, right? If you follow edges, you're eventually gonna lead yourself to 8. So we're going to be talking about a topological sort, and what differs that from a regular sort is that there's multiple ways you can. There's usually multiple ways you can do a topological sort. Not always. The homework there's only going to be one topological sorting, but in the example we're looking over here, there's many ways to do a topological sort of graph. And the topological sort of the graph is you order the vertices in a directed acyclic, and this only works for directed acyclic graphs. That's another thing. You can only do it on directed acyclic graphs. So the sorting is that you order the vertices such that if you've got an edge between two nodes, U and B, that basically the node U appears before V. This has to be true for every single edge in there. So for instance, in the previous example, 0, 1, 2, 3, 4, 5, 6, 7, 8, in other words, listing all the vertices in numerical order, is a valid ordering of the graph because let's look at the edges. 0 comes before 1. 1 comes before 2. 1 comes before 5, right? So if we list them all in order, that's a valid topological ordering. Let me go ahead and just put some other orderings on the board and see if those are topological sorts of this graph. So let's say, so 0, 3, 2, 4, 6, 5, 2, 7, 8. So is this a proper sort of this graph? No. I see people shaking their heads. So 0, there's an edge between 0 and 3, so 0 does come before 3. There's an edge between 0 and between 3 and 6. 3 does come before 6, so those kind of things are valid. And 0 does come before 2, and I forgot 1 here. 0 does come before 1, and 1 does come before 2. And 4 does come before 6. 2 does come before 5. 5 does come before 7, right? There's an edge between 5 and 7. So all we have to check is basically for things that there's vertices between 0 and 4. But let's see. Is there any mistakes here? Are there?
Are there 2 2s?
Are there 2 2s? Yes. Remove this 2 over here. Let's go ahead and remove this 2 over here. So now, is it a valid topological sort? No, because we've got a 5 before a 2, right? And what's the topological sort? And what does the graph say? You've got you have an edge from 2 to 5. So because you have an edge from 2 to 5, this is not a valid topological sort. Now let's swap that around. 0, 3, 1, 4, 6, 2, 5, 7, 8. So let's go ahead and what I'm going to do is start checking off edges manually on the slide. So 0 comes before 3. It comes before 1. 0 comes before 4. 1 comes before 2. 1 comes before 4. Does 1 come before 5? Yes, it does. Does 2 come before 5? Yes, it does. Does 3 come before 6? Yes, it does. Does 4 come before 6? Yes, it does. Does 4 come before 7? Yes, it does. Does 5 come before 7? Yes, it does. Does 7 come before 8? And 6 come before 8. So this appears to be a proper topological sort of the graph. So, so this appears to be a topological sort of this graph. Right, notice that we'd have to go, by the way, that it doesn't matter what I write up on the board. If 1 isn't the first thing that I have down, it's not a proper topological sort because, if 0 isn't the first thing I have down, it's not a proper topological sort. Because if I put like 1 down first, you're going to be in for a world of hurt. Because you need 0 before 1. So the question is, how do I generate a topological sort? Confirming it, you can see how to confirm it. It's just rather tedious. You have to check all the edges. But how do I generate a topological sort? And you know, there's your book has an algorithm, which I find is kind of straightforward. You perform a depth first search of the graph, and then you list the vertices in reverse of their finish order. But honestly, I don't find that particularly exciting or interesting. Instead, what I like to use is something called Kahns Algorithm, K-A-H-N. It's fairly straightforward. I like to use it because it's another way. But you can use this technique of just doing a depth first search and then list the vertices in the reverse of the orders that they're finished in. In other words, I believe that's the order in which you pop them off. So reverse of the order that you pop them off of your stack as you're going through. So that will work. But I like to do Kahns algorithm, which is pretty simple. It says that for let me put this on the board because it's easier when to see how this works when I put it on the board. 0, 3, 4, 5, 1, and 2. Okay. So I've got this graph. I'm going to do a topological sort of it using Kahns algorithm. Kahns algorithm is pretty simple. You have a list of all the vertices, which you have basically 2 data structures. One is a set, and it keeps track of all the nodes that have an in degree of 0. So there's 2 terms now to learn: in degree and out degree, which we're only really learning from this algorithm. In degree is the number of edges that are going into a node. So for instance, 6 has an in degree of 2 at the moment, right? Because there's 2 edges that go into it. It has an out degree of 1 because it has 1 edge that goes out of it. In degree, the number of edges going in; out degree, the number of edges going out. I mentioned this because your Java Jung library has a method that, given a node, you can get the in degree and out degree of a vertice. So 0 has an in degree of 0, but an out degree of 3. Okay. Now Kahns algorithm says basically we keep a set of all the nodes that have an in degree of 0, and we remove them, one of them from the graph, and add that node to the list and then we return the list as our output. That's all the algorithm is. So let's look at all the nodes. Which of these nodes? The only thing that has an in degree of 0 is 0. So we write down 0 and we remove it from the graph, like literally remove it. So in most libraries, if you remove a node, it will remove all accompanying edges as well. So now we repeat. Now we reevaluate what are the nodes that have an in degree of 0. 3 has an in degree of 0 and 1 has an in degree of 0. Right? So that means we can either remove 3 or 1. It doesn't matter. I'm going to go ahead and remove 3. Okay. The only node now that has an in degree of 0 is 1. So that's obviously the next one we're going to remove. So we can either remove 2 next or 4 next. Which would you like? Let's remove 2 next. So now we have 2 and 5. Let's go ahead and remove 5. And now we have only one node that has an in degree of 0. Only one node that has no edges leading into it. So that's 4, so we remove it. And then we have 2 nodes that have an degree of 0, 6 and 7. So remove 7. Now we have 1 node that has an degree of 0. 6. And then we have 1 node that has an degree of 0. And we removed everything. So we're done. That is a topological sort of the graph. So finding a topological sort is different than finding all topological sorts of the graph, and that's a bit of a pain. But really all I'm concerned with is understanding what a topological sort is and how do you find one. Kahns algorithm is a great way to do it. You can also use it doing depth first search. It's not a particularly hard thing. And we can use this basically so if we're using this on like a course prerequisite chart, this is how we can basically say to generate your schedule. Like we can say, okay, we want them to take like 2 major classes each semester. So you take these 2 courses, then you take these 2 courses, then you take these 2 courses, then you take these 2 courses, right? That's how basically, so because this will gives us an ordering of what order you can choose your classes in, right? Like when we give you like kind of a suggested, right? Typically there's a suggested course plan we hand to you saying you should take these courses your first semester plus these electives on these, and stuff, right? And that's kind of how we generate these things. We just look at how many courses you need and what what prerequisites will lead into one another. Probably don't use topological sort to do that, but we can. So that will lead us up to, so now this leads us to the last homework of the semester. Euler, Project Euler, problem 79. Passcode derivation. So this probably looks this will look nothing like you're gonna probably wonder what the heck this has to do with your thing, but this is your last assignment. So a common security method that we use for online banking is to ask the user for 3 random characters from a passcode. So for example, say your passcode to get to your bank account is 531278. Okay? We might ask you to enter in your 2nd, 3rd, and 5th characters, so you'll give us 317, right? Because that's the 2nd, the 3rd, and the 5th characters. If I ask you for characters 1, 2, and 3, you're going to give me 531. If I ask you for characters 2, 3, and 4, I'll 2nd, the 3rd, and the 4th, you'll give me 312. If I ask you for the 2nd, the 4th, and the 6th, you're going to give me 3, 2, and 8. Okay? One thing I'm never going to do, that I mentioned right over here, given that the 3 characters are always asked in order, one thing I'm never going to do is I'm never going to ask you for the 3rd, 2nd, 1st, or the 6th, 5th, and 4th. Okay? Or I might ask you for the 2nd, 3rd, and 5th, but I'm never going to ask you for the 3rd, the 2nd, and the 5. Right? It's always the 3 characters are always going to be in order. So this is a weakness for the security system. So here's a text file. Somebody's password that they've logged in 50 times, that we've got 50 successful logins, right? And our job is to piece together their password, the shortest possible password from this. I don't know why it's cutting off on the edges there. So let me see if I reduce it. That does not help at all. So there we go. If I zoom in even more, it helps. So, okay. So here's a file that has 50 successful login attempts. It's just a file of 50 numbers. The numbers are not separated at all, right? So this means that somebody asked, that we asked the user, and the user pushed in 319, and they were able to log in. We don't know what characters 3, 1, and 9 correspond to, but what do we know about the relationship between 3, 1, and 9? 3 is before 1, 1 is before 9, and also there go, 3 comes before 9. Not something we do have to add to that. It's kind of implied by that relationship. And so we also know that the password contains a 6, an 8, and a 0, and the 6 in the password comes before the 8 and the 0. The 6 comes before the 8 comes before the 0. We also know that we've got a 1 that comes before an 8 and a 0. That means that we know that the 1 comes not only before 9, but the 1 also comes before the 8 and before the 0 as well. Yes?
So do we not account for passcodes that have more than 1 1?
So that's an excellent question. Given that 3 characters are always asked in order, analyze the file to determine the shortest possible secret passcode of an unknown length. So the shortest possible one, by definition, can't have any repeats. Okay. So we're going to assume no repeats. We're determining the shortest possible secret passcode of an unknown length. So the question is, what the heck does this have to do with the topic I just went over? topological sorting? And the answer is that this is just a graph problem, right? So remember what a graph is. It's about relationships, defining relationships. And so the things in this are the individual characters in the passcode. And the relationship between these characters is which one comes before the next. So 3 comes before 1. Let's treat each individual digit as a vertice. That means there's an edge between 3 and 1 and an edge between 1 and 9, right? 3 comes before 1, 1 comes before 9. Then there's a relationship between 6 and 8 and 0, right? Go ahead and draw it for you guys. 3 comes before 1, which comes before 9. 6 comes before 8, which comes before 0. 1 comes before 8, which comes before 0, right? 6 comes before 9, and 9 comes before 0, right? Notice that it's a directed acyclic graph. 1 comes before 2, which comes before 9. So let's put 2 out here because I'm sure there's going to be more connections to 2. And 6 comes before 2, which comes before 9. Right? So we're just going to build up this graph. So let's look at the program we have to write for this. You could solve this one by hand. I mentioned that before. You can solve this one by hand. And there are some repeats in here. Right? But the idea here is that we'll use these to build a graph, right? Read each line, split each line, and go through each character and convert that into like a string or convert that into a node. And then say we've got an edge between 3 and 1 and an edge between 1 and 9 if it doesn't already exist. Then create an edge between 6 and 8 and an edge between 8 and 0 if those don't already exist, and so on and so forth. So use this to generate a graph. The nodes are each individual digit, and the edges are, well, if this one comes directly before this one, generate an edge. Okay, fairly straightforward on that. So then we have to generate the passcode. Well, we have a graph now, so you can either use the def first search to do this, right? And get the reverse finished order. In other words, give me the order that they've been popped out in, but then reverse that to give me a passcode. Or you can use Kahns algorithm, which is iterate through your vertices, find the one that has no in degree of 0, or remove that, and then remove that one, and repeat until you have no edges left. And print them, and you might want to print them out as you remove them too. That's your last homework in a nutshell. But it brings together a lot of things, and the reason I go through it is because A, it's close to the end of semester, and B, the individual components can be slightly tedious. Reading the file, as you know, and splitting it up can actually take an annoying amount of time. But also building the graph, one of the things I mentioned earlier with Jung that sometimes gets forgotten is that when you add an edge, right, it will fail if you already have an edge of the same name, right? So for what I suggest doing is the name of the edges. I would call the edge between 3 and 1 the string 31. So represent your edges with strings, and I'd call edge 31 31, and I'd call edge between 1 and 9 1 9. And that's what worked for me. And basically, if we had a repeat, well, it was like, okay, so I'm just overriding the one that I already have. So that's what worked for me for that one. So that will be worth 100 points, and then there's 50 points for doing Dijkstra's as well. And those are your last homeworks. I will make them do, let's say the last day of class. So that basically so I'm not getting into trouble by having stuff due during this time. Of course you can turn in anything late during this time and demo anything late during this time. But, please demo before the 8th. Okay. And as far as office hours are concerned, I'll have to see whether I'll be in office hours on that Wednesday, but we'll see. All right. So congratulations. You have made it to the end of data structures. Okay. I will take note that the classroom was packed at the beginning. And this may just be that this is not how many students withdrew. They're just made people who, there's probably a lot of people who just didn't show up, you know. But
speaks to the convenience of your online lectures.
It does, but I do that for so many reasons, and I mean it really does. If that does mean that people skip out on my lecture, you know, because of convenience, you know, that's the trade-off I'll gladly take for people who are sick not showing up to my lecture. You know, that's much easier to deal with. And honestly, also, it's much more useful for students to have the lectures because your attention span is really only good for 15 minutes before you have to refocus, and then, you know, it's useful. Unfortunately, it does mean that basically all of my missteps are forever immortalized on the internet, which is terrible, right? Like I see the other professors and they come in with like a small like page, and they don't seem to like make any mistakes because I guess they rehearse or something, and I don't have time for that to rehearse. I know what I'm doing from one lecture to the other because data structures is a fairly linear course to teach. Okay, so we've got 25 minutes left. Let's not put that to waste. You probably want to get started studying for your final exam. So the good news for you is I already have a small study guide. You can find it under data structures, on the class GitHub repository under data structures, and you just click on study guide. And it's just something I wrote last semester, and you'll want to download it because it has some links in there. So I mentioned what programming topics you should probably just make sure you understand. One thing we didn't go over this semester, I think I mentioned it in this class, is how to turn a heap into an array in O of n time, right? Use the bottom-up method, but that's not really something I'm going to focus on too much. But here is where the bulk of what I like comes from. So links from other institutions. I have 4, right? I don't write a practice final for my final exams. I generally prefer the other way, which is doing this. Data structures final exam, right? And then, okay, Princeton has some data structure final exam. Now, the issue is that, of course, just like Temple, there's data structures and there's data structures and algorithms, and some courses, which is an algorithms course, but some, courses, they like split the difference. Like they'll teach merge sort and quick sort in the algorithms class, but not in the data structures class. But, so if you see something that's like completely incomprehensible when you're doing this, it's generally because it's not because it's not because you missed it. It's because that's probably not something that we went over. Like here, the algorithm data structure, analysis of algorithms, right? They're going over big O notation, which is something we went over. Oh, graph search. Give a topological order by running through the for search-based algorithm and listing it in reverse post order. Minimum spanning tree, something that is covered in our book, but we didn't go over. That's mainly something in algorithms we go over. Shortest path in Dijkstra, that's something we go over. Sorting stuff, regular expressions we didn't go over, right? Right? There's some stuff familiar in here and some stuff that's completely unfamiliar in here, right? And that's because it's a data structure. It's like, this is an algorithms course. This is what you'd take after you'd learn about the course with linked lists and stuff, right? And it also goes because we have different, topics. Like, we don't teach binary search tree. We don't teach the self-balancing stuff in this course. Let's see, solution to final class exam from UCS Washington. So there's all sorts of things, and you just got to be aware that basically that not everything in data structures is necessarily an actual stuff that you would know about. Like this is for the algorithms course. Okay. Here are some things that are explicitly on an algorithms course. So I'm going to start by going over the practice final exam I found from Harvard. So I like this one because it's a lot of multiple choice questions, and they go over a lot of stuff that we've gone over in the past. So I'll start with here. So let's go ahead and start. Multiple choice, specify up to 2 answers. And that's a nice policy where you can specify 2 answers, and your first choice, if you get your answer wrong, right, if you're split between 2 answers, put one down as your first choice and one as your second choice, and we'll give you credit if half credit if your second choice is right. So that's kind of a nice way to kind of implicitly put a curve in. All right, so let's go through this. So suppose that items A, B, C, D, and E are pushed in that order onto an initially empty stack. Okay, I understand that stuff, right? Then pop it 4 times, and as each item is popped off, it's inserted into an initially empty queue. If 2 items are then removed from the queue, what is the next item that will be removed from the queue? So if you're having trouble following that, that's okay. That's because this is a visual problem, and we are doing this in words, so obviously the solution to that is to draw, right? That's what I'm going to do. I'm not going to bother trying to solve it in my head. I don't have anything to prove. Okay? So we push A, B, C, and D in that order onto an initially empty stack. So A, B, C, D, and E. So E is at the top of the stack. And then it says we pop 4 times, and insert items in that order, in the order we pop them, onto an initially empty queue. E, D, right, Q front to back, C, and B. So we pop it 4 times. Okay. And now, if 2 items are then removed from the queue, okay, E gets removed, D gets removed. What is the next item that would be removed from the queue? C. Not too hard of a question, right? Makes fairly consistent sense. Okay. That makes consistent sense. All right. If a binary tree is below is printed in a pre-order traversal, what will the result be? So what is the order for pre-order? What is a pre-order traversal? What order do we go in for nodes? Right? You have in order, post order, and pre-order. Right? In order is left, self, right. What's pre-order? Self, left, right. So we can initially knock off 3 of the answers, right? Anything that starts with a 9, that's not a pre-order traversal, right? Because the first thing we visit in pre-order is the root. So it's got to be 6. So 6, and then, so it's root, it's the root, left, and then right. So root, so 6, then 17, then 9, then 4, then 22, then 16, then 12, and that's E over here. Oh, this is something we covered like only on Monday. A graph implementation that uses a 2D array, so that's an adjacency matrix, right? To represent the edges would be most reasonable for which of the following cases? So remember, adjacency list versus adjacency matrix. What we care about is whether you want to use an adjacency list if it's sparse, and an adjacency matrix if it's dense. And it's dense if we're getting closer to basically using up, if basically we're getting closer to v squared number of edges. Sorry, v squared number of edges, where v is the number of vertices. And what's the cutoff point? I said basically after 25%, you want to, if 25% of all possible edges exist, then you want to use an adjacency matrix after that point. So let's see. So 1,000 nodes to 1,200 edges, 100 nodes to 4,000 edges, 1,000 nodes to 10,000 edges, 10 nodes, 20 edges. And none of these, since a graph can only be represented by a linked data structure. Well, we know about linked lists, and we know about adjacency matrices. So adjacency lists and adjacency matrices, so E is invalid, right? So that's just to throw you off the trail. So let's look at this. So if we've got 1,000 nodes, that means there's 1,000,000 possible edges, 1,000 squared, right? So 1,000,000 to 1,200, right? 1,000,000 nodes, 1,200 edges. That sounds pretty sparse to me. Okay? So 1,000,000 possible edges, 1,200 edges. It's pretty sparse. 100 nodes, 100 squared is
10,000.
10,000. It's a small number, as comparatively speaking to 1,000,000. So, and there's 4,000, so 10,000 possible edges. 4,000 of those are used, so that's 40% of what we use. So that's more than 25%. So that's probably the correct answer. Let's check the other ones. 1,000. So again, 1,000,000 possible edges. And this time, 10,000 of them. That's still only 1% of the possible. That's still a pretty sparse graph. And then 10 nodes and 20 edges. That's 100 possible edges, 20 of which exist. That's still considered a sparse graph because we're only using 20% of the possible edges. So answer B is our best answer because 40% of the possible edges exist. It's a dense graph at that point. Okay. So they don't do generics there. So a binary tree is constructed of nodes where they have, you know, a value, an integer value. So we're assuming that we're just working with binary trees that hold integers. Okay. So you construct a binary tree using a node left and right and value. So consider this following method. Public static node mystery. Node root. So we've got this mystery thing that that takes in the root of a tree or subtree and returns a node. If we have a right node, sorry, if we don't have a right node, so in other words, if our right child is null, let's return, we'll return ourselves. So if we don't have a right child, we return ourselves. Otherwise, we return the output of mystery on our right child. So if we have a right child, we call this method. Otherwise, we return ourselves. So what this sounds like is that it goes all the way to the right and returns the rightmost node, right? And what the rightmost node is what? In terms of if all the nodes hold integers, then that integer is the biggest integer, right? All right. So obviously though, that's what I like about this question is that it goes in a completely different direction. So we consult 3 supposedly tech-savvy consultants, and we get 3 opinions about what the method does when we pass it the root of a binary tree. Consultant 1 says it returns the last node that would be visited by an in-order traversal. Consultant 2 says it would be the last node that's visited in a post-order traversal. And consultant 3 says it returns the last node that would be visited by a level order traversal. What's a level order traversal? It's not something I bring up because it's until graphs. So even though we're in the last stages of the class and we're in review technically, I still get to teach you new stuff. So a level order traversal, if we've got a binary tree, a level order traversal looks like this. D, E, F, G, right? Just making sure I knew my ABCs there. So, all right. So we've got a level order traversal. So an in-order traversal of this would do, D, B, E, A, F, C, G, right? Would do my left, then myself, then my right. Right? We're assuming that we're assuming that the letters in here aren't the values. They're just labels for the nodes. Okay? They're not values. Okay? A level order traversal, on the other hand, goes across the levels. So the first node that we would visit is A, then B, then C, then D, then E, then F, then G. That is exactly what it is. It is breadth first search, which is why I don't teach it during the trees section. Because going level order is breadth first search, which means we don't use recursion for it or a stack. We use a queue to do this, right? That's why I said that 90% of the 90 to 90% of the of the traversal for a tree, you just use the in order, post order, or pre order. This is that other case, doing level order, which works completely different. You use a queue because it's a breadth because you. At that point, you treat your tree like a graph. Because remember, trees are graphs. They are special. They are just special graphs that can be arranged in a special manner. Okay. So we've got our opinions here. Which of these opinions is correct, regardless of what the contents of the tree? In other words, which of these opinions is always correct? So. Consultant 1 says it returns the last node visited by an in-order traversal, right? Our algorithm basically finds the largest item in the tree. It finds the rightmost thing in the tree, the largest item in the tree. So the in-order traversal, right? That's always going to have the last thing that's returned by an in-order traversal is going to be the largest thing in the tree, right? So Consultant 1 is always correct in this case. Consultant 2 says it will return the last node visited by a post-order traversal. This is not always correct because the post-order traversal, right? In our example here, the last node in a post-order traversal, it returns the root, which is A, which is very often not the largest thing in the tree. So now the level order traversal. Now in the example we have over here, it does return the rightmost node, which is the largest thing in the tree. But if I remove this, then the last thing returned by a level order traversal would be F, right? Which is not the largest thing in the tree. So consultant 3 is not correct in this case. So the answer is 1 only. Only consultant 1 is correct in this case. All right, question 5. When we have a poorly chosen hash function, it is possible to have a situation in which the search time of a hash table of n items goes to. So what happens when we have a bad hash function? What happens in the hash tables? I saw you make a symbol there. You get collisions. You have things collide when you have a bad hash function. Ideally, like right here's an example of a bad hash function, right? Hash function h of x, where x is the key, is equal to 0. That means that we're going to get, that's a bad hash function because because all the items are going to collide at index 0, right? And in that case, if we're using open addressing if we're even using chaining at that point, right? If we're using chaining, we're just slapping it onto the end of the linked list at index 0, which means the search time for an item would be searching that whole linked list, which contains all the items in the tree, which is O of n. If it's open addressing, we're looking for the next available space, which means we basically we inserted the first item, then the second item, then the third item, and then we'd have to iterate through all the items, which is the same thing as basically adding it to the end of a linked list anyway. So it takes O of n time to do that. So a bad hash function would result basically in everything colliding. So it would take O of n time to search that hash table, which is why when we write a hash table, we assume we're going to use a good hash function, because it's otherwise going to not be worth it. Because then we're just burning a bunch of way too much memory to get linear time lookup. So this is actually where I got one of your questions on the first exam. Nodes for a doubly linked list look like this, just as a reminder. Right? They have a next and a previous. All right. So suppose we have a linked list where we've got node n, we've got node p, and then we've got this third node hanging out at the end. So which of these following expressions are not the third node in the list? So p.next, that gets to the third node in the list. n.next.next, that's the third node in the list. p.previous.next, that gives me p. So that's incorrect. p.next.previous.next, so p.next, that's the third node. .previous, that's p. .next, that's the third node. So d refers to the third node. And n.next.previous.next gets me the third node as well. So the only node in there only one in here that did not give me the last one is C. All right. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so that it can be determined very quickly whether or not that license plate is in the database. Okay? Speed of response is very important. Efficient use of memory is also important, but it's not as important as the speed of querying that database, right? So in other words, time is more important than space here. So which of the following data structure, but that's not to say that memory is not important. Which of the following data structures would be the most appropriate for this task? A sorted linked list, a sorted array of 1,800 entries, a hash table with space for 1,800 entries, so open addressing using 1,800 entries, a hash table with open addressing using 3,600 entries, and a hash table using open addressing with 10,000 entries. All right. So, which one of these is best for our purposes? So a sorted linked list, to find any item in a sorted linked list, well, it's a linked list, so I actually, even if I was trying to do binary search on this thing, I'd have to go to the middle which would take me O of n time, and then I'd have to go to the middle of whatever subsection, which would take me O of n over 2, and then O of n over 4. So a linked list is not the answer. A sorted array with 1800 entries, I could do that, and I could do a binary search, which would get me the answer in log n time, right? So that's much better. Open addressing using 1800 entries. So I'm trying to search for something using open addressing in 1800 entries. That means, and we've got 1800 license plate numbers. That means the hash table is completely filled up. So in this case, it's like trying to find your car, where you parked your car in a completely full parking lot, right? Even though you might know relatively where it is, right? That's what the hash function does. It tells you relatively where it is. You have to search a bunch of cars before you can actually find your car, right? You know, in a full parking lot, it's hard to just see your car. And that's kind of what happens in the hash table over there. You get when it's completely full, you have collisions all over the place. On the other hand, if it's only half full, using 3600 entries, then our equation says that basically we can expect to have 1.5 comparisons that we need to do. In other words, we'd expect only no collisions or one collision, so single lookup or one collision, and then we can return it. That's what that. So, you know, using basically you burning. So basically, we use twice as much space as we need, and we get basically constant time lookup. 10,000 entries would be like even quicker, like we'd be using only 20% of the space there, but the memory cost at that point doesn't really justify the speed up. So the best thing would be D, a hash table with open addressing using 3600 entries, because we're looking at 1.5 steps to look up something, and that's going to be faster than log n time, where the expected runtime defines, where the runtime defines something in that case is, well, we're searching 1800 items, so and this is log n time, so let's see. So split that in half, you're at 900. Split it in half again, you're at 450. Split that in half again, you're at 225, and you're at 3 steps now, and you still have 225 items still left to search. So that's going to be slower than case D. All right, so we will go ahead and pick up here on Monday.